Okay, think about this for a second. The last time you were on a plane or just scrolling through your phone, we are completely surrounded by technology that's so complex it might as well be magic. And, we barely even think about it. I mean, on one hand, you have the raw power of a jet engine with thousands of parts all working in perfect sync. And then on the other, you have this tiny little microchip with literally billions of transistors crammed into a space smaller than your fingernail. These things don't just happen by accident, right? They are the result of some seriously meticulous engineering. So that brings up the real question. How in the world do engineers take an idea from just a sketch to a real physical thing that can handle incredible stress, work perfectly for years, and be made over and over again? How do they know it's going to work before they even build the first one? Well, to get that answer, we've got to start with the people who make it all happen. And it's not just one person, it's a whole team of specialists, and every single one has a critical job to do. So let's start with a really key difference. You've got material scientists. They're the ones asking why. They're digging down to the atomic level to figure out why a material is strong or light or conducts electricity. But then you have materials engineers. They're asking how. How can we take that discovery and use it to build a better engine or a faster chip? The scientist finds the potential, and the engineer makes it real. And of course, in the world of our electronics, you have the semiconductor engineer. These are the architects behind those little microchips we saw. They're the ones who dream up, design, and perfect the tiny circuits that are the brains behind pretty much everything we use today. So what's a day in the life actually like? I love this quote from a materials and processes engineer. It just says it all. It's not just theory, right? It's analyzing failures, supporting production, dealing with corrosion. As they put it, they put out a lot of fires. It really shows you that engineering is, at its heart, a hands-on problem-solving gig. Okay, so how do these engineers, these firefighters, stop problems before they even start? I mean, you can't just build a billion-dollar jet and hope for the best. They need a way to test their ideas, and that's where the digital world comes in. This reminds me of something called the Marshmallow Challenge. It's funny, kids almost always beat adults at it. Why? Because adults plan and plan and plan, and then their tower collapses at the last second. Kids just start building. They test early and they fail fast, and they keep improving their design. It's a lesson engineers have totally taken to heart. And simulation is basically the engineer's version of what those kids are doing. It's this incredible digital tool that lets them build and test and break their designs in a virtual world. They can crank up the pressure, change the temperature. They can see exactly how it'll act in the real world long before a single piece of metal gets cut. And the results? They really speak for themselves. A survey from Tech Clarity found that engineers using simulation build 51% fewer physical prototypes. Think about that. That's half as many expensive models. They also come up with more innovative designs and cut down their testing time. This is a total game changer for how we build stuff. One of the most common tools they use is called linear static stress analysis. Now, it sounds complicated, but the idea is actually super simple. You digitally push and pull on a part to see if it can take the heat, and more importantly, to find its breaking points. And this is what it looks like. It's awesome. The colors on this model show the engineer exactly where the stress is highest. Those red spots are the hot zones. It basically makes invisible forces totally visible, letting them find weaknesses with unbelievable precision. So with this kind of superpower, what can they do? Well, they can test out different designs, they can add a little material where it's needed most to make it stronger, and they can take away material where it's not needed. That's called lightweighting. They can even digitally swap out materials to see if it works better with aluminum or, say, titanium. Then there's another really critical tool called modal analysis. See, everything has a natural frequency that it likes to vibrate at. If a part on an engine has the same natural frequency as the engine's vibration, well, it's bad news. It's like an opera singer hitting that perfect note and shattering a wine glass. Modal analysis helps engineers find those dangerous frequencies so they can design around them and avoid disaster. But look, a perfect design in a computer is only half the story. You still have to actually build the thing in the real world. And for that, you need the perfect materials. This is where the materials engineer is absolutely essential. Seriously, you can have the most amazing, optimized, super strong design on screen, but if you pick the wrong physical material, one that rusts or can't handle the heat, the whole project is a failure. The digital and the physical have to be a perfect match. So what are these materials engineers doing all day? They're really in the thick of it. They're approving every single paint, primer, and finish. They're solving rust problems on older products. They're writing the rule books, the material specs that everyone else has to follow. And they're working on the cool, cutting-edge stuff like 3D printing. At the end of the day, as one engineer put it, they're the people you go to. They're the ones you ask when you have no idea what glue or coating or metal to use for a really specific job. Their knowledge is just indispensable. All right, so we've got the people, we've got the tools. How does it all fit together? It's not a straight line from idea to product. It's a nonstop cycle of innovation. In a field like making semiconductors, it is all about this loop. You start with a concept. You simulate it to see if it'll work. Then, and this is key, you get your teammates to look at it, to challenge it, to find the problems. And finally, you write down everything you learned, and you start the whole cycle all over again, getting a little bit better each time. And that review step, you just can't skip it. It's absolutely crucial. Like this quote says, peer reviews are integral. Fresh eyes always catch mistakes. Working together leads to better solutions and ultimately a way, way better final product. Engineering is definitely a team sport. And finally, documentation. Okay, doesn't sound glamorous, but I promise you it is the backbone of every single successful project. It's the official record of every decision, every test, every change. That's how you fix problems later on, and maybe most importantly, it's how you make sure future engineers can build on your success instead of making the same old mistakes. So what's the big takeaway here? Modern engineering isn't about some lone genius having a eureka moment. It's a powerful cycle that brings together human experts and incredible digital tools, letting teams solve ridiculously complex problems together. And that leaves you with some pretty exciting questions, doesn't it? This combination of smart people, powerful simulation, and amazing materials is what built the world we live in. So what's next? What huge global challenge are these tools going to solve? And what revolutionary new material, something we can't even imagine yet, is a scientist about to discover? The cycle just keeps going.